In the last video, we covered introduction about RAG. In today's video, we will check embedding, indexing, normalization and common embedding models. In the last video, I explained about the simple architecture of RAG. In this architecture, we are using a vector database to save the embedded data. So do you ever think, can we use a normal database like MySQL, MongoDB for this purpose? Why should we use vector database? The reason is, when we search in the database, we should get similar content, not the exact keywords. Postgres, MongoDB, MySQL are good at storing and querying structured data, but they cannot compare meaning of sentences. Basically, these databases do not support semantic search. Semantic search means search by similar meaning. Semantic search finds information based on meaning, not exact words. In short, semantic search understands what you mean, not what you type. Vector database support semantic search. That's why we use vector database for RAG. To find meaningful text or content from the vector database, first we should save this content in the vector database. That is where the embedding comes in. An embedding is a numerical representation of data that captures its meaning. In simple terms, an embedding turns text into list of numbers so a machine can understand and compare meaning. So we should change our text data into numbers. So here, we are not saving the actual text, but in the form of numbers. In vector database, similar meaningful words will be in similar area. Here you can see a three-dimensional vector where the words dog, cat are in the similar area, and the words banana, apple are in the similar area. So in the vector space, similar words or similar meaningful words will be in similar area. So once you do the embedding, your data will be also transferred into numbers and lie in the similar areas based on meaning. To convert our data into vector format, we should use an embedding model. This embedding model actually converts this data into numbers. There are multiple types of embedding models: text embedding, image embedding, video embedding, etc. In this series, I am only talking about text embedding models. Now we can check some of the embedding models that are available. OpenAI text embedding, Google Gemini, OAGAI are some of the famous embedding models. These are paid models and they are also have better performance. Open source models are also available. Models like BGE, Qwen, GTE models, etc. These are open source embedding models. Selection for embedding model will depend on different factors. We can use local embedding models or API based embedding models for our purpose. We can use local or open source models when data privacy matters or you want to know API cost. In this aspect, you can choose open source or local models. Some of those models are BGE, E5, MPNet, etc. We can also choose API-based embedding models if you want best quality with minimal setup or latency and cost are acceptable. So best choices are OpenAI text embedding, Cohere embeddings, etc. Also check for language support. If you want only English, you can choose embedding models for that. Otherwise, choose multilingual models. For English only, you can choose BGE, E5, MPNet, etc. For multilingual, you can choose Cohere, Labs, Multilingual Mini LM, etc. So never use an English only model for multilingual data. Selection of the embedding model also depends on the hardware. So you should ask these questions. Can I run this on CPU? Do I have GPU? How many documents am I embedding? For small or base models, you can use CPU. For larger models, you can use GPU. Consistency rule. So same embedding model should be used in both cases, for both documents and for user queries. Same embedding model and same normalization. So basically you should use same embedding model for user's query and for the document embedding. Once the data is saved in the vector database, we can retrieve that data. Data is retrieved from a vector database by comparing the meaning of a user query with stored embeddings and returns the closest matches. The vector database compares the query embedding with stored embedding using a distance method like cosine similarity. Cosine similarity is a method used to measure how similar two vectors are by comparing their direction. It looks at the angle between two vectors, not their size. Value close to 1 means very similar meaning. Value close to 0 means not related. Value close to -1 means opposite meaning. Cosine similarity is used to find text with similar meaning in semantic search. There are other algorithms to find semantic search like nearest neighbor, Euclidean distance, etc. But we don't need to worry about that. Basically, you need to understand this is the way how the data is retrieved from the vector database. Normalization. Normalization in RAG means scaling embedding vectors to the same length before comparing them. It means making all embedding vectors the same length. This helps the system compare embedding fairly. After normalization, similarity depends only on meaning, not on bigger numbers. That is why normalization is used in semantic search and RAG. In this example, sentence A embedding is like this and sentence B embedding is like this one. Both means the same thing, but sentence B has bigger numbers. After normalization, both becomes the same number. Now the system can see the same direction, same meaning, no confusion caused by bigger numbers. Now what is indexing in embedding? You already heard about indexing, right? In normal database indexing, it is like a table of shortcuts. If you run find all users where email equal to xyz@gmail.com. Without an index, the database scans every row one by one. It slows as data grows. With an index, the database jumps directly to matching rows and fast even with millions of records. So the idea is don't scan everything, use a shortcut. Now, how the vector indexing works. Imagine embedding as points on a huge map. Each document chunk is equal to one point. User question is another point. You want to quickly find the closest points. Instead of checking distance to every point, the vector index groups nearby points, builds smart shortcuts, narrows the search space fast. This is exactly what approximate nearest neighbor algorithm do. Indexing make documents easy to retrieve. Instead of comparing a query embedding with every stored embedding, an index helps the system find the closest ones fast. Without indexing, the system must compare against all vectors. Search becomes very slow as data grows. With indexing, search is much faster, works well even with millions of embeddings, enables real-time semantic search in RAG. Indexing makes semantic search fast and scalable, which is essential for production RAG systems. Normal DB indexing helps you quickly find the right rows. RAG indexing helps you quickly find the right meanings. That is the whole idea. Now we can check these terms again. Embedding, normalization, indexing, cosine similarity. How it works in RAG. Embedding, turning text into meaning, basically documents into embedding and user question into embedding. Normalization, making embeddings fair. After embeddings are created, they are normalized, makes all embedding the same length, removes size differences, keeps only the direction. Indexing, making search fast. All document embeddings are then stored and indexed in a vector database. Indexing organizes embedding, creates shortcuts, avoids checking every embedding. Cosine similarity, finding closest meaning. When a user asks a question, the question is embedded and normalized. The vector database compares it with stored embedding. Cosine similarity measures how close the meaning are. So in a single line, embedding creates meaning, normalization standardizes it, indexing makes it fast, and cosine similarity finds the best match. That's how they all are connected inside a RAG system. So that's all about today's video. I hope this helps. Then please consider to subscribe the channel and like the video. Thank you for watching and see you in the next video. Bye.